information seminar. Today's speaker is Michalis Skotiniotis.
Perfect.
First attempt, no? That is a new member of this group. He will join us in February as a new Hamon. Michalis is an expert in quantum information, quantum signaling,
metrology,
cryptography,
this kind of stuff, yes.
Yes, he made his PhD in Calgary,
yes.
Granada. And then he made a postdoc in the University of Innsbruck under the supervision of Barbara Kraus. And he has been for the last 7 years, I think, in the Autónoma of Barcelona. And now he's looking for a nicer place, so joining us. And he will talk us about symmetry in quantum information.
2 people from Innsbruck already.
Thanks.
2 people, yes.
Yes.
It was a cult.
More so than you think, Juani. So yes, thank you. It's a pleasure to be here, and I'm looking forward to starting. I like the city quite a lot for the time being, and so on. So yes, as Danny said, last 7 years I've been in the quantum information group at the Autónoma. Okay, and most of the stuff I'm going to tell you about today is work that was done during these 7 years. So the approach I took here is to, I guess, kind of introduce myself work-wise to all you guys, just show you a flavor of the kind of problems I work with, okay, what kind of things I'm interested in, the kind of problems that I will be working on, and if people are interested, then of course I need help, so please help me. Okay, so the other thing I wanted to do is to also make the talk a little bit fun. So the first question is, does anyone know who this person is? Anyone have any idea who this person is? Churchill. He's not Churchill. He's too thin to be Churchill. Yes. So this gentleman here is Ludwig Mies van der Rohe. He's a very famous architect. Okay. I like to show you a bunch of his buildings, and I like you to pay very, very close attention to the style, okay? So here's the first one, is the National Gallery in Berlin, okay? Here's another one, this is the Seagram building in New York City. Some of you, if you visited, you've seen this one. He's also very famous for building the IBM Plaza in Chicago. His most famous building is this one here. It's called the Farnsworth House in Chicago as well. And something that's very close to me is also built a pavilion in Barcelona, okay? So I don't know if you notice the buildings and so on, but there is a statement that I have to 90% certainty attributed to Mr. van der Rohe, and the statement is the following. Finally, he said that symmetry is but aesthetics for fools. Now, if you saw the buildings, this to me sounds like somebody who treads the line between genius and complete moron. It's like either he's making fun of me or he doesn't know what he's talking about. Okay, so part of this talk is almost like a response to this kind of the statement, which I find outlandish, considering that I work on symmetry. Also, Danny works on symmetry. I don't know, this would be quite terrible. So here's an outline of what I'm going to talk about. Okay, the first thing I'm going to do is I'm going to tell you why, in my view, one needs to draw a line and distinguish between quantum theory and quantum physics. I'll explain what I mean by these two things in a bit. Okay, then I don't know how much people know about symmetry, so I thought I'd just give you a little bit of the basics of the kind of tools that we'll be using. In particular, I want to mention, you see me use this Schur-Weil duality a lot. Okay, so I'll explain what this is. And then I wanted to go through 3 problems that use this symmetry. The first one is about replicating and compressing quantum information primitives, so states, channels, gates, and so on. The second one pertains to quantum statistical inference. So I'll tell you a little bit about what is quantum parameter estimation, and then I'll show you one particular problem that I'm working on now, which concerns imaging of incoherent point sources, okay, and how symmetry plays a role there. And finally, this is one of my personal favorite papers that I've ever written, which is about why we cannot see macroscopic quantum phenomena in the real world. Okay? So here we go. So quantum theory versus quantum physics. Why do I make a distinction? Because to me, quantum theory is a bona fide mathematical theory. Okay? And just like any good mathematical theory, it can be written down with 3 axioms. The first one tells you the objects of interest of the theory. In this case, we're talking about positive operators of bounded norm. Okay? like this. Here, the next axiom tells you how to compose objects of the theory. So in quantum theory, we do this via the tensor product. And the third axiom tells you how to go between objects in the theory, okay? And in quantum theory, this is accomplished by something called a completely positive trace non-increasing map, okay?
The third action has a sub-action there.
Which sub-action?
There are 4 actions there.
No, there's 3.
Okay.
Okay, well, I'll explain why I lumped them into 3, because for me, measurements are also a special way of this, okay? So trace non-increasing because I demand the following. The first one has to be true, okay? Whatever this map does, it cannot increase the trace of a density matrix. And the second one is complete positivity. This you will recognize as a Choi-Minkowski isomorphism. It basically says that the extension of the map has to also be positive, okay?
All right, is there a difference between trace non-increasing map and trace preserving map?
Yes. So if you write trace non-increasing maps, you're allowing also the use of quantum instruments. So things that don't do complete measurements. Yes, exactly. So this is the reason why. So if I write trace preserving, I can't include the measurements. If I write trace non-increasing, I can't include the measurements. So here's just so I show you what these trace non-increasing maps are. One example is that you all know is a unitary evolution. This is a completely positive trace preserving map. Okay, it's given by this form. And this is a unitary operator on the space of linear operators, okay? The second one that you know is projective measurement. So imagine I do a measurement, but I don't learn the outcome. Then what I would describe this process by this map here, okay? These PKs are projectors. It means they are positive, they're orthogonal, and they sum to the identity, okay? So here's the non-increasing part. There's fine graining. In other words, if this instrument performs a measurement and then I go look at one of them, okay, but I don't know about the other parts of the measurements, then what I get is a subnormalized state. So its trace becomes less than 1, okay? And the last one that you might not be familiar with is the Born rule and generalized measurements. So in quantum theory, you can do more general things than just projectors, okay? And then the Born rule is essentially just this map here. It's a map that takes operators and maps you into real numbers between 0 and 1. And these operators EK here, they are called positive operator value measures, something that takes a positive operator and produces a value measure, a probability for you if you want. And they have the property that they have to be positive and they have to sum out to the identity. They do not have to be orthogonal, okay? And in fact, they don't even have to be the same dimension as the system. They can be arbitrary, okay? That's quantum theory for me, just this. And like if I were to teach it in a course, that's what I would teach. I'd say these are these 3 things, okay? Just with these 3 things you can prove a lot. For example, you can prove the non-cloning theorem, you can quantize entanglement. You don't need to mention anything about physics at all in order to do a lot of quantum information, okay? Just these 3 things, okay? So what do I mean by quantum physics? Quantum physics goes all the way back to Einstein. Quantum physics is when we draw a mental arrow and say this axiom corresponds to this physical thing, okay? So for example, what you do is you say the objects of interest provide a description of elements of physical reality. You say this row that you write down describes the position of something, the momentum of something, the energy of something, all these things, okay? And then the completely positive trace non-increasing maps, they describe physical processes. So some things like interactions or measurements and so on, okay? But this correspondence is rather naive and it's not perfect, okay? Because in order to do physics, you have additional constraints, namely the fact that, for example, physical quantities correspond to Hermitian operators, but not every Hermitian operator corresponds to a physical observable quantity, okay? That's one. And the second one is that physical quantities are subject to additional constraints. I have to impose conservation laws on them, okay? I can't do anything I want. Okay, so for example, the most famous one, and the one that we normally use is Noether's theorem, that the existence of a symmetry implies a conservation law. So you know that if the system is time invariant and there's conservation of energy, translation invariance is momentum, rotational invariance is angular momentum, and there's even more, okay? You have invariance under charge parity time, you have Lorentz symmetries, you have chirality, okay? The physics is the same for right-handed and left-handed people. And the one that I will be using a lot is exchange symmetry. So you have Bose-Einstein versus Fermi-Dirac, for example. You know, things that when I switch them around, they stay the same or get a phase. So all these things are not in the quantum theoretical formalism. You have to use this if you're going to do physics, okay? Good, so then let me tell you about these symmetries and these conservation laws, at least mathematically how we treat them. So you start by saying, okay, let me have a space of operators. So here it's HD, okay? And then closed system evolution, normally you describe it by a set of all D by D matrices that are unitary, okay? If you take this set, then it forms a group under matrix multiplication. In fact, it forms something which people refer to as a representation, or a unitary representation of a group, which I normally write like this, okay? And now, any unitary representation is reducible if you can find a subspace of the original space that's non-trivial, okay? Such that for any state I pick in this subspace, when I act with every element of the unitary representation, I stay within that subspace, okay? That's this condition here. If this is true, then you say this representation is reducible. If you cannot find anything, any non-trivial subspace, then the representation is irreducible. Irreducible representations are to representation theory what the prime numbers are to number theory. If you know the irreducible representations of any group, then you can construct all the representations you want. And the reason is because of these two very famous lemmas by Shor. Okay, I won't go through them, but they basically just essentially define the characteristic traits of irreducible representations. And then you can use them to prove a very important orthogonality theorem that tells you if you take two unitary representations that are inequivalent and you twirl, this is what this integral is called, then you get orthogonality. Okay. So far, so good? Okay. So this essentially tells you that any unitary representation you give me, there exists a basis in this Hilbert space that I can decompose it into several blocks. Each block has irreducible representation, and these irreducible representations that can appear a certain number of times. That's called the multiplicity. Okay? It is convenient for us to write this in a more elegant way using this virtual tensor product. So if this alpha L is 2, for example, for some lambda, then this is a two-dimensional identity. If it's 4, the four-dimensional identity, and so on and so on. Okay? And because your unitary representation which acts on your space has this decomposition, your entire state space also carries this decomposition. Okay? And these H lambdas here, they're called the irreducible subspaces. You can further decompose them into this virtual tensor product, just like here. If you are from condensed matter or high energy physics, then these M lambdas, they are normally called the nuclear spaces. In my case, they're called the carrier spaces, the space that carries the irreducible representation U lambda. And these N lambdas are called the color spaces or the multiplicity spaces, the spaces where they just carry the identity. Okay? So, what is Schur-Weil duality? You now consider that you have several, like the composition law. I have several Hilbert spaces. Each of them identical, I have n copies of it, okay? Now, this space, this total space here, it carries the action of two fundamental groups. The first one is the special unitary group in d dimensions, so the rotations we've been talking about so far, okay, which acts in this way. And the second one is the permutation group. I can always switch the labels of these Hilbert spaces. Now I can permute them round. Okay, this is this T representation here. Now, it should be fairly obvious to realize that I can permute and do these unitaries in any order, which means that these two representations, they commute. In mathematical terms, you say that the unitary representation is the centralizer of the permutation group and vice versa. Each representation is the center of the other. Okay? And then, since these two are representations, they each impose a block diagonal structure on the Hilbert space. Now, in principle, this block diagonal structure is different. But because of this, there's a famous theorem by Schur and Weil that tells you that the blocks in this decomposition under the action of the two groups are in one-to-one correspondence. In other words, the irreducible representation labels of one group can be used to label the blocks or the other group. Okay, they're the same. Two of them are connected. Okay? So here the lambda are the irreps of SUD, or if you want the irreps of Sn, okay? And of course you have that ML, in this case, this representation space carries the irreps of SUD, and this other space here carries the irreps of Sn, okay? So prime example, if you're a physicist, is if you take two systems and you know that you have a singlet and a triplet, right? When you compose them together. So the singlet is permutationally invariant, so it carries this representation. Sorry, the singlet carries the trivial representation of this. The triplet are all permutationally invariant things, so it carries the non-trivial representation of this. And then the ML is the fact that the singlet has one state, which has no orientation, and the triplet has three states, which are the Z components, okay? Good. This is just Schur-Weyl duality. That's all I'm going to use for the rest of this talk, okay? I'm going to show you how to use this trick to do a lot of stuff, okay? So the first one is about replicating and compressing quantum information primitives, okay? So let me tell you first, for example, you should know the very famous result that quantum states cannot be copied. It means that there exists no machine for which I input any state here psi and some ancilla, and out come two copies of psi. You cannot do this. It's impossible, okay? But what you can do is you can do something called super replication. In other words, I give you n copies of this, or n can even be one here, and some ancilla, and there exists a machine that will produce a state for you in some larger Hilbert space such that the overlap of this state with m copies of the original is close to 1, okay? Notice the difference is that this state here could be very much entangled, okay? So in other words, if I were to trace out and ask what is the fidelity of each copy, it might not be as good, okay? But overall, it's good.
Sorry.
Yes?
M is larger than n here.
M is larger than n here, yes. Right?
This is a kind of recall?
A kind?
It's a kind of recall of the input feed?
A recall?
Recall. Remember.
So the protocol, that the way you do this depends on what kind of inputs you have here. Okay, so the big question in super replication is, you give me a family of states here, does there exist such a machine that can produce this? Okay?
So this is a kind of overlap.
This is the overlap, exactly. This is the overlap of phi with m, with the tensor product of m copies of the original.
One, this means that you are recalling that one.
You are
Recalling.
recalling? No.
Remembering.
No, because m is bigger than n. I'm actually producing more copies of it.
You are copying.
I'm copying in some sense, yes.
Making copies.
Yes, that's why it's called a replication. I'm replicating it, or cloning it.
Does this work for any n, or when n becomes big, it works?
There are several versions of it. There is 1 to n, okay? This is known that for certain families of states, you can have a probabilistic protocol that indeed does this. It depends. The rates, and the machines and the rates depend on the family of states you pick and the kind of a protocol that you implement, okay?
Okay, yeah, so in the example above, you have 1.
Yes.
Only 1.
So 1 to 2 here. This one here is impossible.
Can you achieve that in there?
I can do a 1 to 2. I can give you a state phi with probabilistically is very close to these two, yes.
Okay, good.
Okay. So indeed, this is my next slide. A deterministic super replication protocol for arbitrary states does not exist, okay? So if I don't give you any promise and I tell you any state, okay, super replicated, it's impossible. However, if I restrict to a subset of family of states, for example, these ones here, which are very, very famous because they're normally called clock states. These are the states that are important when you do this Ramsey interferometry, okay? So if I tell you that the state I'm giving you belongs in this family, then there exists a probabilistic super replication protocol, which given n of this, will produce you n squared of these, okay? Or I should be more precise, a state whose overlap with n squared copies of this is 1, okay? Probabilistically, okay? The way that you do it is actually very simple. You just employ a probabilistic filter. So essentially you do a measurement. If you succeed and you get a flag, then you have it, okay? the price you pay is that the probability that this filter succeeds, especially if m and n are very large, goes exponentially down. So the more copies you want to replicate, the less likely it is that you will succeed. Okay? Good. Now if you think of this protocol, okay, in a different way, what you're essentially doing is the following. I give you this gate here, and what you do is you input here the plus state, and out will come your psi of theta, the one that you want to replicate, okay? This is essentially the previous protocol. And now you can ask, well, okay, what if I just want to super replicate the gates themselves? In other words, I'm not restricted to putting plus here. I can put any state I want here. And I can do whatever I want here. And at the end, what I want is to have, if you give me n copies of this gate, I want to produce a gate V whose overlap with m copies of this gate is close to 1. Okay? And you ask, is this possible? And the answer is yes, it's possible, and it can be done deterministically. Okay? And here's how you do it. The idea is, again, to exploit sure-while duality. If you look at this unitary here, you'll notice that the only thing that really matters is the Hamming weight, or the number of excitations. So let me go back. You see, this is 0, this is 1. Every time I see a 1, I put an e to the I theta. Okay? So the only thing that matters here is how many 1s there are in this string. So m here is counting the number of 1s. And then this here is just the way that these 1s are permuted. I don't care about that. Okay? So what you do is the following. You realize that, well, if you give me many copies of this, the distribution, you see this thing here is a binomial. The distribution of this approaches a Gaussian. And then the replication protocol is the following. Do the right thing on the typical subspace of this Gaussian, i.e. the bulk, and then forget about the rest. Okay? Just do some random thing here. Okay? It turns out that if you do this, and you compute the fidelity of this protocol with u theta tensor m, you can prove that this fidelity tends to 1 so long as this alpha and beta, they are basically telling you how big is this bulk, how much of this bulk do I have to copy. Okay? All of it, half of it, fraction of it, and so on. Okay, so when you do this integral, you show that this fidelity goes to 1 if these two numbers are like this, i.e. if m is n squared, which is remarkable. Okay, so think about it the following way. IBM charges you to use this gate. You pay to use this gate 100 times, but then you use it 10,000 times, okay, for the same amount of money. Nice, no? So actually, it turns out that you can super replicate an arbitrary gate in SU2, okay, deterministically again. I remind you, if I gave you a state on the block sphere, you couldn't super replicate. But if I give you a gate that does arbitrary things on the sphere, you can super replicate. Okay? And the nice thing is that it actually really works. There was a photonic implementation, particularly of our protocol with the U1 gate in this paper here, where they actually did, okay, they did a 1 to 2, but they did it, okay? And they showed that it works. Okay?
So what is the use of this method?
So the use of this method is that, I want to, like I said, if I charge you.
Experiment. What they want to replicate in the experiment.
So what they wanted to replicate in the experiment is this unitary. They put a unitary, and I don't tell you theta. Huh? So for any theta, without knowing it, they managed to say, okay, give me one use of the gate, and they managed to come out and show you that what they produced is something which is very close to 2 uses of the gate. Okay? Which is very nice. Okay, so this is where we're left. Okay, so then you can ask similar things, but for states. For example, if you run this protocol backwards, this is equivalent to asking about whether or not you can compress quantum states. For instance, if I give you n copies of ρ, how much quantum memory do I need in order to store the information in this state? Okay? So again, we have the sure-while duality. Remember, everything resides essentially here. This here just carries the permutations. So you can throw this guy out, okay, and just store things that are here, right? So, but this, as you know, the dimension of this grows very, very large, so you're saving quite a lot by throwing this away, okay? In fact, we can prove the following. This was not us, this was actually the group of Giulio Chiribella. You can show that if rho is a pure state, like the clock states that we had before, okay, then all the pertinent information relies on the permutationally symmetric subspace. In fact, only one subspace here, okay, the one with maximum angular momentum. And this subspace is of dimension n plus 1, so you need a memory which is log 2 of n plus 1, okay? Log 2 of n versus how much, if I give you n qubits, the state space is 2 to the n. That's an exponential compression. That's a lot, okay? You save quite a lot.
Yeah, sorry, but all this compression comes from the symmetry.
Yes, exactly.
Another way of seeing it would be that you can block diagonalize the density matrix, and n is the information, and n is how many blocks do you have.
Exactly, and you throw away the blocks since all the information is in the blocks.
Are the same,
Exactly, exactly. But if the state is pure, you only need one block, right? Because it's now, if the state is mixed, okay, and you know the spectrum of it, it turns out that you need the same amount of memory. In other words, if you're across all the blocks, but you know the spectrum of your initial state, then again you only need log n memory. If you don't know the spectrum, the only thing you have to do is add another half log n. This half log n comes from the fact that you basically need to sample from a distribution, which is learn a little bit the spectrum, and then from this sample store. Okay, so this is the extra thing. But this is remarkable. I don't know anything about rho, okay? And I only need this many quantum bits to store it.
Can I ask you 2 questions here?
Yes.
So one of them is, this in quantum computation will ask about the efficiency of the protocol.
Yes.
And it looks to me like this must be inefficient. It will take exponential time. Or do you know
No,
anything about
this is efficient. In fact, this paper here is Chiribella and Hayashi. They actually proved the strong converse of this.
Okay, then I'm confused about the requirements. You can make, if this works, you can have like a logarithmically small amount of states compressed and then use the protocol to produce more. Like magic, for example, I'm thinking about magic states, which are useful in quantum computing.
Okay.
And if you have a computation with not so many magic states, you can classically simulate it in a
Yes.
supercomputer efficiently. And so you need a big number of them. And I'm confused whether it's possible here to take n magic states, reduce them into, just have a logarithmic amount of them, and then create more efficiently.
Create more states out.
Yes, or maybe
No,
it's
it's not that you reduce the number of magic states, it's that you reduce the dimension of each.
Yes, exactly. Especially, so you say, I give you many copies of a state and the information is kind of like very loosely spread over. And then what you do is you concentrate this information as much as you can in the smallest possible register, and then you store it in that smallest register. That's essentially what you do.
But are magic states permissionally?
Permissionally invariant? Do they have any symmetry?
normally when you have a computation with Clifford gates, you have n copies of the same magic state. You can promote a computation to universal.
As soon as you have n copies, then there's permutation symmetry. So in principle, you should be able to do a similar thing.
Magic states is what allows you to do more computation. And maybe it's about, there is something here about the operations they're using that doesn't allow them to. There is something I didn't understand here, but I will ask you later.
Well, the other thing is okay, the other thing I forgot to mention is, remember, this protocol has to work for all, it has to be universal. In other words, it has to work for any state you give me in here,
Yes.
right? So, and the symmetry is really important here because this is what so you have to, all your protocol has to explode is a symmetry. It doesn't need, it cannot know anything else, okay?
The other question I have is, in quantum money protocols, I guess you cannot, non-cloning is important for not breaking them. So, but there, the states that they use are typically different, right? So this is what doesn't allow you to break quantum money with this.
Yes, I'll give you another reason afterwards, actually, for this. But it's true, yes. So, for example, you may wonder in the super replication protocol that I told you, right? If I give you n copies of the gate, and you do parameter estimation, for example, then you know that the precision can be 1 over n squared if you use an entangled state. And then you can argue, okay, I super replicate it, to n squared, and then I do the precision, I get n to the fourth. It turns out that that's not possible. Why? Because the states you need to do the Heisenberg limit, they are not in the bulk. So they're in here, and in here you're doing completely the wrong thing, okay? So the only reason why you super replicate is because on average, you do the right thing. But for the particular state, it's you get screwed, okay? So other things that sure while duality allows you to do is probabilistic storage and retrieval of n unitary gates. Okay, this is a very interesting result. I give you n unitary gates, and there is a probabilistic protocol where you can store n unitary gates in one and then retrieve them out, okay, in a probabilistic manner. And the other one is that there is a deterministic compression of n unitaries in an exponentially smaller register. In fact, this follows from the super replication. If you see U tensor n, I can always compress it into a single unitary, but on a larger d-dimensional system, okay? And I can also retrieve it out afterwards. So there's a interesting, fascinating field where people are trying to use this to do all this kind of nice stuff, and what is the optimal rates and prove strong converses and so on, okay, about how much you can compress a given family of states or unitaries. Or the thing that nobody has looked at and we are looking at now is super replication of quantum channels. Okay, you can probabilistically super replicate states, I told you. If they are unitary gates, then you can do deterministically. What about if they are channels? Okay, so for example, when I say channels, I'm thinking of things, for example, that are open system dynamics. Okay, dynamics that have to do with open quantum systems. Okay, and the question here becomes, if I give you n copies of such a quantum channel, does there exist a machine? This machine M is normally called a quantum clone or a quantum process tensor, okay? Such that this machine converts n copies into some other channel whose fidelity again is close to 1. Okay? That's what the task is. And the example, just to keep in mind, the gain or amplitude damping channels. So these are open system. If you want to think of open systems, it's spontaneous absorption and spontaneous emission. Okay? These channels have a very nice property in that they satisfy a global symmetry. In fact, they satisfy this global symmetry. If I rotate the initial state, apply the channel, and then do the inverse rotation, I get the channel back. In fact, I can even make these angles here different. So this theta can be different from this theta, and this will still be true. Okay? And this happens for all rho. Okay? So you can play the same trick. There's a sure-while duality here. This time the Hilbert space is not H tensor n, but it's the space of linear operators. You can decompose it like this. All the information you want is in here, and you throw away this register. Okay? And then you ask, okay, can I copy now this kind of thing? So this is ongoing work with a collaborator, Elena Korianova in Akoki, and a PhD student in Nakateha in JIT, where we're looking at whether or not we can do this. And we are very close to proving it. In fact, I'm fairly certain that there is no deterministic super replication protocol for CPTP maps. It's impossible to do it deterministically. Okay? Now, in the way to proving this, we came up with a protocol that if you're clever enough, you can reverse it and you can prove that there is some compression. I don't know how much, I don't know what the rate is, but the way that the protocol works, I can run it backwards and I can see that I can compress it a little bit. Okay? The other question is, okay, there's no deterministic super replication. Maybe there's something like states. Maybe I can probabilistically super replicate. This I don't know. Okay, we have to look. And then we want to extend this to generators. So this map here, you can always write it as the exponent of some Lindblad operator times time. Okay, and then you can impose the symmetry on E or on L gamma and ask, okay, now if I give you open system dynamics, can I compress this dynamics or can I super replicate these dynamics at the master equation level or not? The interesting question, another interesting question is interconversion. Suppose your open system dynamics have a certain damping parameter gamma, which is very harmful for you. Is there a way that you can change this channel into another channel with a gamma that's more favorable for you, for example? Okay. And there's also similar questions of distillation, whether or not I can distill channels out of this kind of work. Everything follows essentially the same kind of tools. It's just different problems, but with the same tools. And the last thing that we wanted to do is something called a broadcasting of quantum channels. This is another version of cloning, where for states it is known that the only states that you can broadcasting is like a TV station, no? I have a signal, I broadcast it on an antenna, and everyone gets the signal, right? So there's an equivalent statement about quantum states, whether you can do this for quantum states, and the result is only if the states commute, okay? Now for channels, there seems to be a little bit more of a leeway. Maybe we can relax this condition and say, well, they don't have to exactly commute, but maybe not exactly commute, but we don't know. We're trying to see whether or not there is a way that we can do something more here.
What questions for channels are solved for states?
Mostly all the stuff are solved for states and not for channels.
Okay.
So if you, yes, super application is solved for states. So I mean, all this work came from the fact that once we realized this, and then we basically went back in the literature and said, okay, what are people doing with states? Okay, now let's check if we can do it with channels. Okay, that was the idea.
No cloning theorem for channels?
There is something, but I don't think it's called no cloning. But there is a version of it, yes, exactly.
There is one for TV channels. It's called lawsuits.
It's okay. Okay, so this is one work, and notice that here, okay, this is the last place I put physics, but this is a question that required no quantum physics. It was all quantum information, let's say, okay? So the next thing I want to tell you about is something that does require physics, and it's quantum statistical inference. I don't know how much you guys know about quantum statistical inference, so I'll start by very briefly telling you what quantum statistical inference is, okay? If you think of any experiment, essentially every experiment you can break down into the following process. You have a probe, that's a physical system, okay? This probe undergoes some dynamical process that depends on some parameter. So if you think of LIGO, for example, the system is the interferometer. The process is whether there's a gravitational wave going through this interferometer or not, okay? And then you make measurements, okay? You gather data, you do statistical analysis, and from the data you infer gravitational wave, no gravitational wave, this much the mass, and so on and so forth, okay? So if I strip all the physics out of it, essentially the problem is a statistical one, which basically is the following. I have a random variable x, which is distributed according to some distribution, which depends on a set of parameters I call lambda, okay? And what you do is you sample. So you take x from this parameter. You sample and sample and sample, okay? And your goal, and the game is, okay, I give you a sample, now give me an estimate of lambda, okay? So an estimator is a function that takes as inputs what you see, realizations of the random variable, and outputs for you some set of numbers, and this set of numbers are supposed to be your estimate for the parameter, okay? Now, if it's a good estimator, it needs to satisfy two things. The first one is that it needs to be unbiased. On average, this should be the value, no? We don't want systematic errors, okay, on the random. And the second one is the random errors have to be as small as possible. And these random errors are essentially classified by the precision or the covariance matrix of this estimator, okay? That needs to be the smallest possible. Now you will think that this is a hopeless task of all the estimators, which ones satisfy this and so on, but there is a very famous theorem by Kramer-Rao. Yes?
Normally you have enough knowledge about lambda, no?
Normally not, you are correct. So there are two, yes. So I can tell you, so there's two, this goes all the way back to Prague. There are two schools of thoughts. Physicists, in particular when you do gravitational wave detection, you have a model that predicts a value of lambda, so you roughly know it, okay? Also, when you do the pendulum, you know that the value of gravity is roughly 9.8 and you're looking for the extra digits. This is the frequentist approach. The frequentists believe that there is a true value and that you need to estimate it. The situation you're considering is the Bayesian approach. You say, no. It can take any value, okay? And I have some prior knowledge about what this value is supposed to be, okay? And then I use this prior knowledge and then I do my update and so on. Now, everything you do here, this kind of things, they hold also for the Bayesian, okay? The only thing that changes is that in the frequencies, the Kramer-Rao bound is pretty standard. You can have a Bayesian version of the Kramer-Rao bound, but the Bayesian version is very sensitive. If you give me a prior, for example, that has sharp lines, I cannot use this. I have to use some other thing, okay? But for most purposes, if you say, okay, for most knowledge, everything is a Gaussian or a Poissonian, then you can use the Bayesian version of this, okay? Good. So the Kramer-Rao bound basically tells you the following. For any unbiased estimator, the precision or the covariance matrix is lower bounded by this matrix here, and it's just the number of times you repeat the experiment. And this matrix F here is given like this. It's called the average score, okay? This matrix is known as the Fisher information matrix, okay? The important thing about the Kremer-Rao bound is that classically at least, if you're in the asymptotic limit, which if you're a frequentist means that you roughly know the parameter and you're just looking for the extra digits, this is known to be saturable, okay? In other words, this inequality becomes an equality and the estimator is maximum likelihood, okay? That's all you need, okay? Now, everything here was classical. What happens when I go to the quantum Kremer-Rao bound? The only thing that you have to remember is that I have to replace this by the Born rule, which was this here. And now I have an extra optimization condition because I can choose here any set of positive operators that sum up to the identity. That's the power of quantum mechanics, okay? Which means that I have an additional optimization here. And this optimization is given here. I have to maximize the Fisher information over all possible measurements that I can perform. And when you do this maximization, what you get is what's known as the quantum Fisher information matrix, okay? That's the only thing, okay? That's the only thing that changes quantum mechanically. That's simple, okay? Now let me show you an application where you can use this kind of inference network. Now does everyone remember the imaging of two sources? So imagine that you have two stars and you turn your telescope up and you see, on the screen you see blobs of light, and the question is, okay, am I seeing two stars or am I seeing one star, right? And then there's, I don't know if you remember, when we were in high school we were taught that the resolution of any imaging instrument is governed by the Rayleigh criterion. And what Rayleigh tells you is that two incoherent point sources can barely be resolved if the intensity maximum of one lies on the intensity minimum of the other. So for example, here's two point spread functions, two images. Here you can tell, okay, these are two sources. Here you're at the Rayleigh limit. You can barely say it's two sources. And here, there's no way you can say that there are two sources, right? They're two overlapping. And in fact, you can derive from just simple geometrical optics what this limit is. It's the angular resolution, which is what this, if you want to think of it as an angle like this, okay, is roughly the wavelength of light that you are imaging over 2 times the numerical value of the aperture. Okay, this for the pupil, I think this is 1.22 or something like this. Okay, good. Now, but this is a heuristic limit, and it pertains to incoherent sources, and in particular, it pertains to intensity measurements. What you're doing here is you're measuring intensity. You're counting photons. Okay, and then this limit holds. Okay, so the minimal resolvable distance, normally if you buy a microscope, what they give you is something called the SNR, the signal to noise ratio, which is the D over the precision. So that you can see things. Okay. Now, there are a few assumptions that you do when you witness these incoherent point sources. The first one is that they are stars and they're very far apart, so you're in the paraxial approximation, okay? Now, and the second thing you do with incoherent point sources, at least when they are stars, is that you say they're very, very faint and they produce monochromatic light. Very, very faint means the following. It means that if you were to describe quantum mechanically the state of the light that you see, what you do is you say, well, mostly I get vacuum, nothing, and very rarely I get a single photon. Okay, that's what this rho 1 is. And this single photon, it has a spatial profile. In other words, if I were to look at the imaging plane, if it came from the left star, it would be some Gaussian here, and if it came from the right star, it would be some Gaussian here. Okay. So what you do is the same thing you do with the diffraction pattern. If you had a lot of light, you would see this PSF. What is the state of a single photon? Well, you take the square root of that PSF and you put it there, okay? And now this Q and this 1 minus Q are supposed to encode the relative intensity of the two sources. There's Q from the left and 1 minus Q from the right, okay? And here's again what this PSF is, okay? It's just Gaussian, okay? So this is if the star was on the left. This is if the star is on the right, okay? And if you look at it, this should remind you very much of essentially the ground state of a quantum optical harmonic oscillator. That's essentially what you have here, okay? So I have a photon, which is in the ground state of a quantum electromagnetic field, and it's either here or displaced slightly on the other side, okay? Good. Just by definition here, when I write x here, I mean the position eigensets. In other words, eigensets of this creation annihilation operators, okay? So here's the Kremer-Rao again. So what do? Photon comes in, your screen is detectors, a detector clicks, you say, okay, this detector clicked, another photon, this detector clicked, another photon, this detector clicked. You do this many times, you obtain statistics, which are these things here, and then from these statistics, you compute the Kremer-Rao and you extract an estimate, okay, by maximum likelihood. Now, if you do direct imaging, in other words, all you do is count where the photons land, you can prove that this Fisher information has the following. This is for estimating the center of the intensity, it goes as 1 minus d squared, d is a separation. This is for estimating the separation, okay? Now notice that if the separation is much smaller than the width of your Gaussian, in other words, it tends to 0, this goes to 0, and if you remember, I have to take the inverse of this for the precision, so your precision for this blows up, and this is the Rayleigh limit, okay? Now, since quantum mechanically this is direct imaging, this was me doing this measurement, but quantum mechanically I can do any other measurement I want, right? Remember, I have to maximize over all possible measurements. So does there exist a measurement that does better than this? Well, it turns out in 2016, a bunch of people from Singapore found such a measurement. And the measurement is essentially make an energy measurement in the ground states of a harmonic oscillator whose position is at the center. So basically, you ask every photon that comes in, are you in the ground state here or in the excited state? If you do this measurement, then the Fisher information matrix becomes this. Notice how this is now a constant independent of the separation, which means that I don't care how close these stars are, I can always tell them apart. Always, okay? Now this was a very big thing, and people did experiments and they verified that indeed this holds and so on, but this derivation has a lot of assumptions in it. The first one being that it only works if you assume that the sources are equally bright. One.
So that means that if you have two stars very close, in the sky very close, you cannot distinguish with the traditional method.
But with this method,
that there are two stars there.
Yes. Yes. And people did it.
That instead of measuring the position, you measure
the energy. Yes. In fact, this measurement, if you want it, it's called spatial mode demultiplexing. Oops. Yeah. Okay. I'll go very quickly. These are like the Hermite-Gauss modes. So let me see if I can. In fact, the original paper even had the construction. Hold on, sorry.
How you know there are two stars? You only have this method.
Well, okay.
You have to have another different
yes.
method to
Yeah. I mean, again, here you're assuming that, one example where this is used a lot is in exoplanet detection. So you see a star, and from other data you know that there is a planet, and you're trying to find, okay, is this planet in the Goldilocks zone or not? And then you will do this measurement. So this measurement here, they're called the Hermite-Gauss modes, or the Laguerre-Gauss modes. So you design an optical fiber where the center core is the 0th mode, and the outer core is the 1 and the 2 and the 3 and so on. And then you just basically have the photons come in, and then you have detectors. Is it in the cladding? Is it in the center? And this is how they do it, essentially. Okay, it's quite remarkable. I think Ephraim Steinberg was the first one that did the experiment in this way. Okay, so like I said, now the thing is that it only works. These measurements are only optimal under the assumption that the sources are equally bright already. This I don't know. So in exoplanet detection, this is not the case. The planet is not as bright as the star, no? So this method won't work. And the other one is that I need to know, yes?
I understand something. You need to measure all states in all of Hermite modes, or you need to distinguish 0 from the
So in principle, you need to measure all of them, but they show that actually doing if you're in the super resolution limit regime, doing a 0 versus the rest is enough.
Okay, so you can do heterodyne measurements?
No, this is not heterodyne. This is Hermite-Gauss. You have to do Hermite-Gauss. Okay. So the other thing is that it requires you to know ahead of time this position xc. Okay, which means that you need to estimate the center of the intensity. Moreover, not only estimate it, you need to be able to place the demultiplexing fiber right at this position. Okay. Otherwise, if you don't do that, this is something that I proved with my PhD student, you don't get super resolution. So this is this B spate, binary spate. This is the measurement, this ground state versus the rest. Okay. Now the dotted lines here, I increase the misalignment. 0 means everything is perfectly aligned. So you see what happens, this is a perfect measurement. As soon as I'm misaligned a quarter of the way, look at what happens. I go to 0 very fast, and then even faster if I go down halfway. Okay. Now what we did with my PhD student is we did the following thing. We say, okay, imagine I take it as given that is misaligned, and then between the fiber and the detection, I put a linear interferometer and I do some sort of rotations and I prepare some data. I try to correct for this misalignment a little bit, and we managed to push, as you can see the signal to noise ratio, we managed to push it ever closer. Okay? But there is always a sharp drop off. Okay? You can never get it completely to 1.
Can you use this method, for example, to do a better estimation, for example, of the visible matter you see in the universe?
Okay, so this one here only works, so I assume there's 2 point sources.
They are hidden objects.
Okay, that's the other thing. So here, I took the 2 objects and they are coplanar. Okay? Now, it turns out that if you want to do the full 3D thing, it's a little bit harder, but it's still doable. Okay? The biggest problem is that we do not know, or we do not have an explicit expression if there are multiple sources everywhere that emit. Okay? This one is only particular for 2. So, and the reason is because it is a pain in the ass to compute this quantum field. Imagine you have many sources. You have to estimate the centers and then the relative positions of each of them. There's a lot of parameters here. It grows remarkably far. But it's an interesting problem, actually. There's people looking at ways to do it. Actually, I'm looking at ways to do it. Okay. Now, this was a problem for us because I'm not interested in knowing the centroid. This misalignment is an issue for me. I don't, is there a way that I can avoid having to put the device at this location? And the answer is yes. And the way to do it is to realize that photons, they are bosons, and therefore they have exchange symmetry. Okay. So the trick is to take 2 photons that come from the star, throw them on a 50-50 beam splitter, and then put 2 detectors. Okay? Now, is everyone familiar with the Hong-Mandel effect? No? So the Hong-Mandel effect is the following. Imagine that these 2 photons that come here, they are indistinguishable in every possible way. They have the same polarization, they have the same spatial profile, they arrive at the same time. Then you can prove that only one detector will click here. You don't know which one, but only one will click. Okay? If the photons are distinguishable in any way, they don't have the same polarization, they don't have the same spatial profile, then it could be that both detectors click. Okay? So what you do is essentially this. You take 2 photons, you send them here, and you count the number of times the photons bunched versus the number of times the photons, you get a coincidence click. And the reason is because these probabilities, they are related to the overlap of their quantum mechanical states. So if you repeat this experiment, with the frequency of outcomes, you estimate this P, you invert, you estimate the overlap is related to the separation, boom, you have it. And indeed, the experiment was done in Poland, in Warsaw, and this is the result of Tsang, the original one, where you do the spatial mode demultiplexing. And this is for 2 photons, and this is the visibility. So you see, it's not exactly at 0.25, it's actually an 1/8 of the way there, but you still get super resolution, okay? And also, you get the advantage that you can also estimate the centroid if you want. So to do that, instead of just carrying which detector clicked, you register where inside the detector the photons clicked. And then you do it. Good. Now the Hong-Mandel effect is known to do something which in quantum information I knew very well, which is called estimating the overlap between 2 quantum states. Okay? Now, if you wanted to estimate the overlap, what you do here is you do the swap test n times. If you have the same number of systems, you can actually do this much faster and much better, okay? More precisely. So the thing that we were asking with my PhD student is, can we actually do this for super resolution? Just collect a bunch of photons and do collective measurements, okay? In order to estimate the separation. So again, the key is Schur-Wald duality, because if you have many copies of a state, it has this very nice form. You see this probability depends on J. For us, this J depends on the separation of the sources. So what you do is you measure the total angular momentum, like this, and then here's what you get. So if you measure 2 photons, this is the result of Parniak. This is measuring 3 photons, 4 photons, 5 photons. If you go all the way to 50 photons, you've reached the same bound as the people that do the measurements with the demultiplexing, and I don't need to know the centroid at all, okay? Now, I also have the advantage that this measurement of measuring the total angular momentum is weak. It leaves a state behind, and I can use this state to learn even more stuff. For example, I can use it to learn the relative intensity between the 2 sources. In fact, I can use it to do simultaneous estimation of all the relevant parameters, something which is impossible to do if you were to actually do the optimal measurement like they say, okay? Now, you may be wondering if this can be done, and we have a Pathfinder challenge proposal with Michal Parniak, who's the guy that did the experiment with 2 photons, and a bunch of colleagues from Crete, where we propose a design involving a quantum memory and then a multi-port beam splitter, such that we can do this for at least 7, 8, 9, maybe even 10 photons, okay? And the hope is that, well, third time's a charm. Maybe this time they fund us, okay? Let's see. Good. And with that, I don't know how much time I have. I think I need to go a bit faster, or? 5, 10 minutes. Perfect. Okay. So now let me tell you about how to use the Schur-Wald duality to answer a very important question, which is macroscopic quantum phenomena. Okay? So, as you all know, there is nothing in quantum theory that precludes it from being applicable at the macroscopic scale. Okay? There's nothing in Schrödinger equation that says this only holds for atoms or electrons. Okay? But I'm sure that you all agree that we do not see macroscopic quantum phenomena in our everyday lives. No? My computer is not in a superposition. I don't see entanglement in macroscopic things. Okay? And the reason is also that if you apply naively quantum theory at the macroscopic scale, you also get these bizarre things with Schrödinger's cat and Wigner's friend and things that make no sense. Okay? So to explain why you don't get macroscopic quantum phenomena, people came up with all sorts of reasons. The most famous one is decoherence, or Zurek's Ein selection principle. The idea is that the environment is constantly measuring you, and then you collapse always to the measurement Ein selection basis, and that's it. This is the reason why. Okay. The second one is that, well, your human organs are rubbish detectors. You know, they're not very efficient. Your eyes are not very efficient. There's this famous quote by Feynman that said that if your eyes were 10 times more sensitive, you'd be able to see like quantum effects in light, for example. And the third one is that people say, well, if you are talking about macroscopic systems, then you have to include gravity. And as far as I know, there is no theory that incorporates quantum theory and gravity. So people add phenomenological models that say it should be like this or that or the other and so on, okay? But for me, the first two, they're kind of a straw man argument, okay? People are getting better and better at isolating systems. Now we've done interference experiments involving molecules and viruses and so on. So this is just a technicality. For me, it's like experimenters are going to get better. They're going to get better at isolating systems. So we should be, in principle, have larger and larger systems at the quantum mechanical scale, okay? And the third one is that, well, I don't want a phenomenology, you know? I'm wondering whether or not I can explain the reason why I cannot see macroscopic superpositions purely from within quantum theory. In other words, the only thing I'm going to assume from now on is that quantum theory holds true, okay? And the fact that I'm in a physical world and there are conservation laws. That's it, okay? So here's how it goes. To start off, I'd like to give you an example. If you did a quantum mechanics course and you probably came across this, if you haven't asked your professor that what he's doing is wrong, then you should go back and ask him now, okay? So here's an example. Consider you have a single mode of the electromagnetic field, and I tell you that this mode is prepared in one of two states, okay? And then you wish to distinguish among them. Now, you recognize that these two states are perfectly orthogonal. So all you have to do is measure in the sigma x basis, and you will distinguish, right? But your lab is a closed system, okay? And you're only allowed to perform things that commute with the total energy. When the total energy is this Hamiltonian here, right? You're only allowed to perform things that commute with this, and it's very clearly sigma x does not commute with this Hamiltonian.
This is the Hamiltonian
Of your lab, the whole thing if you want, no? Everything. No?
It should include the measurement device.
Yes, exactly. So your measurement device, you're trying to do a sigma x, which is forbidden. I mean, you have energy conservation. How the hell are you doing this? No? This violates energy conservation. This is anathema. Why? How are people doing this? Okay? So you were probably taught that, what, you know, if you go to an experimenter, you say, oh, this is no biggie, I do this all the time. No? Okay, but how? I mean, it violates the conservation of energy. How do you do this? The reason is that they hide something from you. The way they do it is like this. In comes the mode of the electromagnetic field. They have a laser that comes on the other side. And then they do photo count and photo subtraction here. This is how they implement the measurement. This laser here is important. It is very important that you explain, even at an undergrad, that this is how we do it, okay? The reason is the following. The laser is in a coherent state, and the average state of a coherent state is alpha squared, okay? What the beam splitter does is it does a unitary exchange interaction. In other words, you get photons hopping from the laser to the mode and from the mode to the laser. This is total energy preserving. No problem there. Photodetectors just count photons. Total energy preserving. No problem there either. Okay? So what this beam splitter does is it entangles the laser with the mode. Okay? Now, if you ask yourself what is the state of the laser field after this interaction, what you do is you take the mode, the system, tensor the laser, do the unitary interaction, and then trace out the system. Okay? And what I'm doing here is I'm computing the overlap of the post of the state of my laser after the interaction with the one before. And what you can prove is that this fidelity goes as 1 over this number here. And obviously, if my laser is very intense, so this is very large, this is very close to 1. In other words, this thing here is this. So you're safe in not including the laser, you see, because it factors out in both cases. So this is the reason why in your physics class the professor does not tell you the laser is there, because of this, okay? If you want to think of it a different way, this is the same as you have a system which has a single quantum of energy and a laser field that has millions of quantum of energy. The reason why you don't include it in the description is the same reason why when I jump off the Earth, I don't use the Earth in the description. It's exactly the same reason, okay? Good. So now, the reason why the laser field is there is because it acts as a phase reference. Okay? A phase reference is any system that has superpositions over the conserved quantity, in this case energy. Okay? Something like this. Indeed, if you didn't have this laser, okay, it would be impossible for you to distinguish whether what you're given is this or this. Okay? And the same holds true with the Stern-Gerlach magnet. Okay? If you didn't have a Stern-Gerlach magnet, it would be impossible for you to distinguish the orientation, whether it's orthogonal or not. Okay? Now, the other thing you should notice is that, yes, in the previous example here, we were safe to ignore this because this was a microscopic superposition. What if I now give you a macroscopic superposition? Something which has, for example, like this. Okay? Wait, did I miss it? No, I didn't. Okay. So the important thing is, as you see, is that if I don't have the reference frame, I don't see superpositions, but this is the characteristic trait of quantum theory. Okay? And it's the one thing that would convince me, okay, if you had a macroscopic system and you told me that this is a macroscopic quantum system, okay, I need to see interference. Okay? Now, interference essentially means being able to see these cross terms. Okay? So, with and without a reference frame, the point becomes, if this is a macroscopic superposition, it should look like this. If you're trying to cheat me, and it's a classical mixture, it will look like this. So I need to distinguish between these two possibilities, okay? This is a very simple problem in what's known as quantum hypothesis testing. I give you two states, distinguish with maximum probability, okay? The probability of success is the probability that you say it's this when it's this, plus the probability you say it's this when indeed is that, okay? And it's given by this expression here, okay? Now, if you put alpha beta equals 1 over square root of 2, and you assume that it's equally likely that I give you either one of those, you can prove very easily the probability of success is 3/4, okay? So you have a 3/4 chance of guessing it right. So here's the macroscopic superposition now. Notice that this is n, okay? And notice that this is 0, 0 plus nn. Now, the way to do this is like before, I need a laser. Only this time, clearly a laser has to be a little bit larger than this, no? If the laser is much smaller, I'm not gonna see this, because this has now as many quanta as the laser. It's like, I mean, I'm the moon and the earth, I can't exclude the earth now, because they're similar size, okay? So, what I demand now is the following. I want a measurement apparatus, i.e. a laser or a Stern-Gerlach magnet, that is classical. What do I mean by classical? I mean the following two things. Any quantum effect that exists here is at the microscopic scale, and secondly, classical things are reusable. I look at my watch, I don't throw it away afterwards. I look at it again and again and again and again before I throw it away, okay? So I need these two, I demand that these two properties, okay? And once again, what I do is, here's my measurement device, here's my system, there's total energy conservation, so by Schur Weil, I block diagonalize it like this, okay? So this is for the macroscopic superposition, this is for the mixture. And then what you do is you say, look, from 0 to n, these two guys, they look exactly the same. They look like this. But for k bigger than n, I have a difference. I have these guys here, okay? And then in order to achieve this 3/4 probability of success, what I can prove is that the size of this laser has to be n squared, quadratically larger than the system that I'm looking at, okay? Now, if this bothers you, actually we did it for the same result holds if you're doing spins or delocalized wave packets. So in other words, Stern-Gerlach magnets, rulers, okay? The size has to be quadratically larger, okay? And we did a very back of the envelope computation, just a tongue-in-cheek to entice the referees. Imagine that you want the Schrödinger cat, it's dead or alive. Imagine that the cat, in this case, this is Ulf, my collaborator is Yelena's cat. Wolf is about 3 kilograms. He's not, he's about 7, but let's assume he's 3. That's about 10 to the 26, he's mostly made out of water, okay? Each water molecule I consider as a spin, so there's 10 to the 26 spins inside Ulf, okay? This is all spins up, this is all spins down. And I ask, what is the size of the Stern-Gerlach magnet I would need in order to see Ulf in this superposition? And the answer is 50 times the size of the Earth, okay? This is why you cannot see macroscopic superpositions. And I didn't include gravity, I didn't include decoherence, I just did quantum theory and conservation laws, okay? Now, you may have noticed throughout this talk this quadratic thing. Quantum theory offers a quadratic improvement in precision. I get a quadratic super-replication. The size of things is quadratically larger, okay? And you may wonder, well, where did this come about? Now, in all honesty, this came out from a brutal mathematical optimization. But you can ask yourself, is there a fundamental physical reason why this is the limit? So this is what you were asking Juani, and the answer is, yes, there is, and we proved that these limits, you can all explain them from the non-signaling principle. If you insist that you cannot communicate faster, that there is a speed limit to information transfer, the best you can get in all these protocols is n squared. And and I should mention that I didn't assume, when we did this paper, we didn't assume quantum mechanics. We just assumed no signaling. In other words, if no signaling holds, no other theory in the future can ever do better at these tasks than quantum theory. Which is remarkable, no? So if I told you that the precision with which you can measure things has to do with the fact that the speed of light is constant and you cannot communicate faster, I mean, what the hell? These two things are unrelated, no?
So if I find a super replication protocol, then I disprove no signaling.
If you find a if you can find a super replication protocol with a faster rate than the one that we gave. So if you gave n to n cubed, then yes, you will break it. Okay. Exactly. Which brings me back to Mr. Van der Mies, or Mies van der Rohe, and this statement here. Now, this statement bothered me when I found out about it. Okay, and then I tried to look if somebody has responded to Van der Rohe in any way, and nobody did. So I decided that I will, and this is my response to Mr. Van der Rohe: that fools are those who reduce symmetry to mere aesthetics. Okay, and I thank you very much for your attention. And if you have any more questions, please let me know.
I have one in the last part. In this, you have to explain me
a little bit. The no signaling.
No, yes, the macroscopic quantum phenomena.
Yes.
You use this Weil-Schur theorem.
Well
What
done.
is the symmetry there?
So
It doesn't work for any system.
yes. So for energy, the symmetry is U1, no phase reference.
Okay, so just the conservation of energy.
Energy, yes. In this one, is conservation of energy. When you go to superpositions of spins, then it's angular momentum. When you go to delocalized wave packets, it is the symmetry corresponding to the Euclidean group. So rotations, translations, and boosts.
So basically, what you are asking the system is to have something conserved.
Yes.
If you have something conserved, then you have a symmetry.
Exactly. Exactly. So I'm saying I'm in physics, there's conserved quantities. I have to play by these conserved quantities. And if I play with this in quantum theory, what is the size that I need in order to do it?
Okay.
And this was the only thing. I haven't done it for relativistic. So I haven't included, for example, the Lorentz group or the Poincaré group, for example. This is something that I would very much like to do because I think maybe things change there. I don't know, for example. Okay. Now, the other thing that I would like to do is even something more innocuous, which we're in the way of doing now. So remember I told you there are certain macroscopic superpositions that this will not detect. For example, something like a noon state, because this is an energy eigenstate and this formalism won't detect it. But for a noon state, what I want to do is, and the way that you can discriminate a noon state is essentially you send the modes here. If it's a noon state, then you will notice that the photon number difference here is never odd. It's always even. Whereas if it's a mixed state, you will get even or odd.
Yeah,
okay?
This depends not only in the state, but also in the measurement or the measurement procedure.
Exactly. So what is the measurement procedure here? The measurement procedure is this beam splitter that has to be 50-50. It has to not impart any relative phase between the two. And with Giulio Gaspari and Jig, we even went more radical. We said, okay, if this is a very large photon state, then there is also photonic pressure, no? So the photons, if the photons are really here, they will push this mirror over, and then I will lose the coherence. So it has to be big enough so that I don't see this motion. So we ask, how big should the mirror be? And this makes sense also in LIGO, because if you look at LIGO, the way that the beam is bolted to the ground, the mirrors are bolted to the ground. And the reason is because they cannot move. If they move, you lose the coherence. So we're trying to explain it also this way. Yes?
So this is just a speculation.
Mm-hmm.
So what will happen? Because I think you assume to obtain these limits for magnet in this experiment. So particular geometry of the space, no?
Flat.
Flat.
Yes.
What happens near the holes?
I don't know.
You have in these very strange bodies in the universe, you have huge magnetic fields. So
I have no. So like I said,
all these results.
All these are non-relativistic. So I assumed non-relativistic quantum mechanics. The reason is because I do not know how to handle the symmetry groups in relativistic quantum mechanics. More importantly, I think it's not even clear when you go close to these curved spacetimes, how do you marry quantum theory with gravity there is not really known. I think this is the reason why people in Austria now are focusing on doing all these experiments. They want to use exactly these ideas, like build macroscopics to probe gravity, to kind of learn about what things happen there. And actually our result is kind of relevant also in their case, because we're telling them, this is the size, okay. Barring all the other things, okay, this is how big your detector needs to be. And I think it will be relevant there.
Another thing is, so you said before that you need a very, very powerful laser.
Yes.
To visualize the macroscopic object.
Correct.
But this will destroy the object, no?
But you don't put it directly.
Powerful.
You don't put it directly. You put the laser. They interact on the beam splitter. So this is also a very strong, powerful object. I mean, this is you, for example. This is a human being, no? And I'm saying that if you want to see the human being in up and down, this laser has to be very, very bright indeed. Maybe, I don't know, the size of a star or something like this. But you throw the light on the beam splitter in principle. Okay, so you don't shine it directly on the. Yeah. Otherwise, yes.
We just wanted to destroy things. Expensive European money. Boom. I think we should go to lunch.
Yes.
Any more questions? So, let's thank Michalis again.
Thank you.
Thank you.